Today's presenter is Natalia Carrillo. She has a bachelor's degree in mathematics, a master's degree in philosophy of practical science at the National Autonomous University of Mexico. She's currently doing a PhD in philosophy of science, and she's going to give a talk on the history section.
Well, first of all, thank you very much for the invitation. I hear this is, of course, organized partly by students, partly by Erasmus.
I don't do anything.
Thanks.
I just listen.
So thanks to all the students organizing this. I think I've never been to anything like this, and this is interesting. And thanks, Jonathan, for having me in mind. So what I would like to tell you about, I'd like to kind of contextualize the explanation we have on reaction potential. I have the understanding that one person gave a talk that had to do with reaction potential, and she explained a few things about ion channels and well, the mechanism behind the action potential. So I'm going to try not to go into too much detail. I'm going to give enough detail to say what I think is going to be interesting, but please feel free, if I'm saying something that's unclear, or either the words or the content, you feel like you would have a clear idea, you kind of raise your hand and interrupt it and clear things out, feel free to interrupt. And obviously to make comments. I'm hoping that we can have eventually like a class discussion about certain issues. So all this to say, like if there's anything on your mind and you want to speak out, please do. I'm thinking about starting asking you a couple of questions that not for a discussion in groups. I think we can do that later, but just so that like you can maybe write down on your notebook like a few reflections on this, which is going to establish like a framework. So the first is like, would you say that the phenomenon of the nervous impulse has been scientifically understood? Do you think it is a satisfactory explanation, the one you've heard? The second is, if you know about any anomaly in our understanding of the action potential, if you remember, I think you read like parts of Thomas Kuhn's structure, and so if you remember, anomalies are things that don't quite fit into the paradigm, right? So do you know about any problems we have with the explanation? And the third is, if you think that it is possible that two different and incompatible explanations of the same phenomenon be equally valid. So if you want to wonder about this, I'll give you like a couple of minutes to just kind of see what you think about it. In this third point, if you have an example, please share it. If you know like a phenomenon that can be accounted for in two different ways.
Light is a particle and it's also a wave. And it has mass, but it doesn't. Sometimes.
That's a very good one, yeah.
More writing. Don't see enough hands moving.
Okay, I guess I'll carry on and just keep these things in mind.
Maps.
So, this is what I'm going to do. I'm going to tell you about two theories that are based on mathematical models that attempt to explain the nerve pulse, right? This is a current debate, so that's why I think that it was like valuable for me to bring this information here, because it's actually something that's going on. It's the wave discussion has some years. This is kind of more recent. And so I'm going to start telling you about the classical model, which you've already heard quite a bit about. So I'm just going to kind of, no?
You mean
Oh, not the model, I'm sorry. The classical explanation, which is derived. So I'm going to talk about the classical explanation just to recapitulate, remind you about the ion channels and the things moving and the membranes, etc. And then tell you what is a little bit of how these two guys, Hodgkin and Huxley, developed a mathematical model of the nervous impulse understood in that particular way. And then I'm going to tell you a little bit about a new model. And then we're going to hopefully have a little discussion around this to see what your thoughts are. So, the action potential, this is a drawing of Ramon y Cajal, this Spanish that used to draw. For him, drawing was a very important way to gain understanding on the neurons. So he spent like his whole life behind the microscope. And as you already know, like we have the neurons connect with other neurons through synapse. Something that's very important to have in mind is that we're just going to talk about how the nervous impulse travels within a neuron. We're not going to talk about synaptic transmission. That's a different phenomenon, and it's a whole different story, right? And it has the axon, which is that long tail, the dendrites, and the axon terminals. And we are most of all going to talk how this nervous impulse travels along the axon, right? All these bifurcations are more complicated to understand. I mean, you can, and it's built upon the understanding you have for the axon, right? But we're going to generally be talking about like a little piece of axon, which is like a cylinder, right? And it has, the cylinder is made from a phospholipid layer, which is, like it's shown here, it's a lipid bilayer, which means that you have, these little balls is a phosphate, and there are two lipid chains, right? And they pair up with another phospholipid on the other way around. And if you put that in a liquid, that tends to organize in lipid bilayers, and so it's basically, it's like an oil bubble with water inside and outside, right? Well, it's not a bubble, it's an oil cylinder. So now we're talking about the axon, right? So you have like an oil bubble cylinder with Gatorade inside and outside, because it's an electrolyte, so it has ions suspended in it, right? And so there are the ions, and it's like this is the part where I don't know how much detail you have. We don't need to understand exactly, for the purposes of my talk, at least. I mean, if you're doing consciousness studies, I think it would be a good idea to eventually understand this very well. But what happens, the explanation we're going to give has to do with the way that ions move across permeable membranes, right? So what does it mean to have a permeable membrane? If you have just a lipid layer, ions will not cross. Do you know why ions will not cross?
Concentration?
Not yet, just if you don't have the proteins.
I was going to say, because the inside is hydrophobic and the outside is hydrophilic, so the sodium doesn't want to go through the middle.
The lipid layer. Yeah, the ions dissolve in water. And generally what dissolves in water does not dissolve in oil. So they cannot cross. They cannot dissolve into the lipid bilayer and come across. So the way that we usually understand, and this is like the textbook explanation of what's going on, right? Is that there are these like proteins, and you know that complex proteins have this three-dimensional structure. And in particular, these proteins that are floating in the membrane, like these, some of these, would have this three-dimensional structure where they have like a pore. And what happens is, the explanation says, these pores, these proteins, can change their conformation so that they let ions go through. So they have two states, open and closed, right? And they're open or closed depending on the voltage, right? And we're talking about voltage because these ions, the Gatorade, so to speak, the ions are charged. So the ions, if you have, for example, membrane and you have more sodium on one side than on the other, and there's only sodium and water, one side is going to be have more positive charge than the other side, right? So that generates an electrical gradient. So if that membrane suddenly becomes permeable to the sodium, then electrical forces will be acting on the ions, and just the diffusion gradient is going to be acting on the ions. So the ions are going to move according to electrochemical gradients, and this determines the dynamics of the action potential. So what we observe, the action potential is characterized as a nonlinear phenomenon, which is a very common term in mathematics and in a lot of biology. And what it means that something is a nonlinear phenomenon is like when you have an obnoxious colleague that's, for example, poking you, right? So I'm sitting next to this guy is like, face, he pokes me twice, and we're like, hey, would you mind not poking me? He pokes me again, I'm like, hey, really, like, seriously, stop it. And then he pokes me again, and I kill the guy. That's kind of a nonlinear phenomenon, right? I mean, you would expect, like, more poking and more of the same response. But if the dynamic suddenly completely changes, then we say, mathematically, that's a non-linear phenomenon. So, like, what happens here with the neurons is that if you stimulate, and this means that you are inserting an electrode, so you're recording and inserting charge into the cylinder, right? How you insert charge is a whole complicated thing, but just imagine that you can kind of insert charge and see what it does, right? Depending on if you insert positive or negative charge, the potential, so you're measuring voltage, and who can explain what measuring voltage means? So basically, voltage is always measured between 2 points. So I'm going to compare, voltage is measured from point A and point B, and what I'm doing is I'm basically subtracting the electrical energy from one point to the other. So if I do it from this point to this point, and this point is more positive than this point, I'm going to get like a positive something voltage. If I do it from this point to this point, I'm going to get a negative voltage. So it's basically, what's the difference in electric potential? That's voltage, right? So we're measuring how much positive is one side from the other in the membrane. That's what we're measuring in voltage. So what happens, and it's interesting, it happens in all cells. If you do that in cells and measure like what's the potential inside the cell, the electric potential inside the cell and outside the cell, it's very common to find that the potential is something. Yeah?
I'm just confused. Are we talking within the cell or inside and outside the cell? Are we talking like transmission through the neuron or between two neurons?
So right now, we're not talking about transmission. Or you could as well, this happens in all cells. So you have to have like voltage sensitive channels, but we're talking about voltage, which means we are measuring the electrical potential inside the cell compared to outside the cell. So like you're close to the membrane inside and close to the membrane outside. So if I had a voltmeter, I'd be like putting one microelectrode here and another microelectrode here and saying which is more positive. And it's normal to detect a voltage, some voltage. In particular, neurons have a pretty big negative voltage that's around -65. So you measure that. And you're wiggling the thing, right? So we're inserting charge inside the cell. And if we insert negative charge, what we see is that proportionate to what, so this is the stimulus, so proportionate to what we're putting in, that's what we get, right? And it only holds the amount of time that I hold the stimulus, right? If I do a positive one, if I do a little bit, this is linear, it's okay. And then if I do a little bit more of a certain number that I can empirically find what it is, but it's around -50, 45, then the thing suddenly goes bananas. And it's like somebody hits me again, and then I take the bat and I hit myself, like, you know? So I'm saying like, okay, get a little bit less negative, and then suddenly it goes like not only less negative, but 0, and then positive, and then back to 0, and then, you know? So this is the phenomenon that we're going to be talking about. This is the way that it has been characterized historically, and I hope I can tell you a little bit of how it is. And so it's a non-linear phenomenon. I hope if you don't take anything home, then at least you know what non-linearity means. And it's all or nothing, right? So maybe you remember this is a non-linear, this is an all or nothing non-linear phenomenon as well. Like if you flush a little bit, it doesn't flush. If you flush a little bit more, some water comes out, and then there's a threshold beyond which hopefully whatever was there is going to go away, right? So the action potential has to do with gates opening and closing across which ions want to. Rasmus is telling you how this is a terrible way to say it, but there are gradients. There's an electrical gradient and there's a chemical gradient. So there's a lot of sodium outside of the cell, a lot of potassium inside the cell, and generally the cell is not permeable to sodium or potassium, but when the gates open, like in the subway, then this like flow of sodium ions first comes into the cell, making it, since it's positive charge going in the cell cell depolarizes, and then eventually those sodium channels close, but the potassium channels open. And then potassium and sodium are both positive, so potassium channel ions coming in actually does the reverse of what the sodium ions, electrically speaking, does the reverse. So the potassium comes into the cell, bringing again positive charge inside the cell. And eventually these channels close, and the potential is stabilized to the resting state. Right? And I like the analogy of the subway because that's how I imagine like electric potential or electrochemical potential is going to be like the people want to go into the subway, right? But as long as the gates don't open, they are not, it's only potential energy. So when the gates open and you see all those people coming in, that's when the potential energy becomes actual, it manifests its desires, so to speak, right? So that's how, and the desires of the ions, the electrical and chemical forces that the ions are subject to, generate this dynamic.
So what exactly happens to the cell in the ion channels when the threshold is reached?
So,
like, does the gate open at that point?
yeah. So gate is actually a metaphor. and it depends on the channel. So this is, I'm going to try and give a little bit of a thing. But yeah, what happens is that you have the membrane here, and you have the channel, right? And one way to imagine it is as if it had like a gate that's going to open and close, right? And it's in resting state, it's going to close. And then when you reach a certain potential, that's around -40, I think, in that image, then this gate opens, right? And there's a sodium channel, and there's another potassium channel. So they are in the kind of protein that sodium goes through is different from the kind of protein that potassium goes through. And why I say this is a metaphor is because, for example, for the potassium channel, what the explanation is really that you know that proteins have like alpha helix and beta plates and all this like three-dimensional. So potassium channels have like 4 transmembrane domains, which if I draw, it's going to just spoil the whole thing. But those things, when the electric field changes, so if it's a lot more positive here than here, it has a certain configuration, and then if this amount of charge changes, then its three-dimensional structure goes, and suddenly ions can move through, for example. So that kind of thing happens, or that's what we say. And then, so this is what we're measuring in one point of that axis, right? So this is not, we still have to account for how this thing travels. So supposedly what happens is that since the ions are coming in, they spread a little bit, they move a little bit towards the sides, which stimulates the labor channels, and they open. And then the sodium that's around that area comes in, eventually the potassium that was inside the area comes out, and that generates another action potential in this adjacent area. So it's like when you drop a stone in a pond, that you would see like the ripples going, you know, like radially. That's how it spreads. So it will spread eventually. So this is, I'm sorry, am I okay? Am I doing okay? Are you bored already? So that's the standard explanation. I guess this is more or less what this other person told you about. Sort of.
They did a briefer version, but yeah.
A briefer? I thought this was a super brief version. Okay. Okay, so what I'm going to try and tell you right now is where does this explanation come from? How the hell do we know? I mean, we cannot see this. So this is we know the DNA sequence of these protein channels. And then we do all these, like, try and infer what the three-dimensional structure is, and we have all these theories about how they change. But how did we get to this particular understanding of the phenomenon? That's what I'm going to try and account for. So the story goes more or less like this. Originally, I mean like in 200 BC, Galen, famous medicine, well, people those days who did everything. Genius, basically, this guy over here. He proposed that that we are animated by these animal spirits that run through our nerves, which were some sort of like magical liquid that runs through all our bodies, right? And his theory survived up until more after Descartes, and it suffered some modifications. So some people started thinking that it was, for example, Descartes thought that this liquid actually filled the muscles, and then that's how they contract, right? So a muscular contraction is really like this animal spirit's liquid filling up your muscle, right? And then some other people, at that time, they were starting to understand fermentation process, so some of the people started suggesting that it's more like the animal spirits kind of ferment, and there's like some chemical interaction with the muscles, right? So one good day, my great-great-great-grandfather Galvani was in his lab, which is this lab, and he was dissecting a frog's leg. You all know this story. And while he was dissecting the frog's leg, a spark came out of an electricity generator and hit the knife. The knife was touching the nerve, and the frog leg contracted, like the leg, not even the frog, right? And this like blew his mind. He was like, wow, what happened here? And he started to do all kinds of things with frog's legs. He eventually discovered that if he took a frog's leg and a bimetallic arc, so that's basically metal type C with metal type Z, touching both the nerve and the muscle, then the frog leg contracts. And this was gained a lot of popularity, not only in the scientific community, but everywhere. Mary Shelley wrote Frankenstein, inspired by the idea that electricity is what animates us. So this establishes like a turning point in the history of our understanding of how the nervous system communicates. And eventually, so in 1935, among other things, is that they discovered that electricity definitely had something to do with it, that there was some sort of intrinsic animal electricity. And then they started measuring electrical variables in frogs, which is very difficult because frogs have very, very tiny nerves, right? I mean, like our nerves, like we can't see them. The technology was very coarse, like not very easy. And eventually this zoologist discovered that squids have a giant axon. Not the giant squid. I mean, the giant squid for sure has a super big axon, but normal squids have huge axons, like to the point of like 1 millimeter in diameter. And that was fabulous because then they could actually insert a microelectrode inside the nerve cell and measure all these like voltage differences like with a very good detail. So this is more or less the giant axon. By the way, the giant axon is giant because the width of the axon supposedly helps the transmission of ions, and they need it to react very quickly and contract the mantle very quickly in order to run away from the prey. So that's the hypothesis. By 1940, people were doing experiments inside, like this is a suspended axon, and they're inserted microelectrodes in it. Ida Hyde, this is like a feminist side note, was the first person to invent a microelectrode. She was the third person to receive a PhD in Germany. The poor microelectrode got destroyed in the war, and nobody ever gave her credit. And then somebody else invented it, like reinvented it, sort of. Marmot, and got the credit for it. So what I want to tell you right now is the story from 1940 up until 1960s, 70s, which is like the boom era of the understanding of the action potential. And it has to do with this is Hodgkin and Huxley, this is a physiologist and a physicist, electrical physicist. And how they arrived at a mathematical model of the nervous pulse. So in summary, we have these ions, we have membranes, we have they didn't know that there were channels, but they did know that somehow ions got across the membrane. And they knew the theory of electrochemical equilibrium and how ions behave across permeable membranes. And what they thought, which was what led them to their discovery, is that they said, okay, so if it's ions moving across a membrane, ions are charged, And in as much as they are charged, they behave like electrical currents. So why don't we try and construct an analogy between a circuit and what's going on in the membrane. So if we were to do that, what could we say? So for example, the channels kind of let current go through, right? So they act like resistances, like an electric resistance. And the voltage that's accumulated on the voltage, which is the potential difference across the membrane, is like having a battery, right? And then the membrane is an isolating material that has charges on both sides, and that behaves a little bit like a capacitor. So a capacitor is, if one plate can become positive and the other negative, and if you disconnect the battery, the charges are close enough to be attracted between each other so they stay there. So it's like a proto, what do you call this?
Battery.
Proto-battery. So they built this analogy, and they arrived and they constructed the circuit that would do the equivalent thing that the membrane does, right? And that's this circuit right here, where G stands for conductance, which is 1 between resistance. And that little arrow means that the resistance is variable, right? Because at first you don't, the channels don't let, well, whatever mechanism, they didn't know they were channels, don't let ions flow, and then that changes, right? Then it becomes very permeable, and then it becomes very impermeable. So these are all devices that exist. Like, you could potentially build this circuit. You actually can't, because the characterization of the way the resistance vary is difficult to build physically. But so what they had is that they had the biological phenomenon, then they built an electrical analog, and from the electrical analog, they got a mathematical model. How the hell did they do that? It's not very good. So what they did is, like, we have laws of physics with which we build equations for electrical circuits. So they just reconstructed the equations that would explain the behavior of the circuit they built. So I'm going to go, don't worry, we're not going to do any maths. But I just wanted you to see, like, which were the laws that were involved. So it has to do with current, voltage, resistance, Kirchhoff, adding the currents, whatever. And they eventually got to this model, which has 4 equations, right? The first has to do with membrane capacitance, V is voltage, this is the conductance of potassium, this is the electrochemical equilibrium of potassium, etc. Sodium, and this is like the leak current, which is like all the rest that they couldn't account for. And then these other equations. So this is a dynamical systems model, which means that the incognita is a function. So what we're going to obtain, the solution, each solution of this system, so each function, voltage, which is a function of time, each graph that solves the system is a state of the membrane, right? So that is how this mathematical model tells us things about the membrane. And then, yeah.
What do you mean by state?
So this, right? So I have some parameter. This would be a solution of the equation, which describes the state of the membrane, right? A kind of particular behavior, I guess, like an evolution of the voltage through time. Okay. So then, Hodgkin, this is from the original paper of Hodgkin and Huxley. So the ones that are unfinished are the calculations, and the ones that are finished are the measurements. So then they said, look, like if I calculate the solutions of my system, so each one of these graphs is a function of voltage of, in time, which is a solution of the system, right? Well, this is actually measurements. Those are solutions of the system, right? And they say like, look, like we really, like it is almost as if we have the neuron in the equations.
Why isn't it finished?
Here.
No, on the top.
No, this is the explanation.
Okay.
The propagated action potential took about 3 weeks to complete and must have been an enormous labor for Andrew Huxley. So basically they didn't have computers. You're a computer scientist, that's why you're like, yeah, isn't the thing good for you? I mean, what else?
Natalia, can you explain the difference between the top and the lower part of the diagram? That went
Yeah.
a bit fast.
So this is a solution of the equations.
What does that mean?
That means that you find a V, like you find a function of voltage that makes all these equations satisfy. So the same voltage function satisfies this one, and this one.
So are you saying that the voltage can only be like discrete select values?
No, the voltage is a function of time.
Not
that's why
discrete, but
this is-
select. It's continuous, but select. So you said discrete and select. You're right about select, you're wrong about discrete. Yeah. Sorry.
Okay. Is that answer? More or less. So the question is, so what I'm looking for in those equations, so I have 4 equations, and I could have whatever function in this universe, well, this is not a function. It has to satisfy certain things, right? But I could make each one of these is a function of time, right? And my formula, you've solved systems of equations, right? When you're looking for one number that satisfies. So what we're looking for here is one function that satisfies, right? So I could say, so this could satisfy and this could satisfy, but this equation might not, this function might not satisfy the system of equations. So that system of equations gives me a family of graphs, right, that would describe voltage in time for the cell. And so it gives me all the possible states, that's why we call them states, all the possible things that the voltage across the memory could be doing, right? And what they found, so they calculated, so these are calculations from the equations, and these are measurements from a giant axon, right, of a squid. And the similarity is clear, qualitatively. Quantitatively, at that time, it was very difficult. It was a lot of work for Huxley, as we already saw, because he had to do the calculations by hand. And what's really surprising about this is that you can actually, now that we have computers, you can stick those equations into a simulator. And there's a simulator called Neuron, which you can go and buy out of your favorite simulation store. And so you give it you paint your neuron here, so you watch it in a microscope and you put it here and you say it's like this and it has like 2 little legs here. And then please calculate how the action potential would behave in whatever part. So this is pretty amazing. I don't know what you think, but this is very impressive. If you are not impressed by this, you are not human. I mean, you can go home. So this gave them the Nobel Prize in 1963. Like the community was baffled. They were like, "This is incredible. These guys like blew it. Science works. We have faith in humanity. Perfect, right?" This is a copy of their original article from 1952, right? This is a pretty old type. The aesthetic is pretty nice. So, geez, okay. Maybe we should stop. I don't know if we should stop here
Have a break?
and have a short break.
Yeah, let's do the break now. That's a good idea.
Okay. So this is all I'm going to say about this traditional explanation. You're going to see why I call it traditional in a second. But I mean, my only point was to kind of recapitulate what is going on in the neuron, how it is that this kind of electrical way of understanding what happens in nerves came about, what it has to do with frogs and electricity, and how it is that way of understanding the nervous pulse, namely like this electrical way of understanding the nerve pulse, led Hodgkin and Huxley to a mathematical model of the phenomenon that actually allows us to simulate the neuron, right? So that's pretty much what I hope that you more or less understood. So now I'm going to talk about another model that came out around 2005 that actually Rasmus originally told me about. Rasmus knows the person that came up with this other model. And it has to do with different physical principles than the Hodgkin and Huxley model. So this other model is going to have to do with thermodynamics. And the paper came out, so this is one of the papers that these guys have led into the wild. And listen, so look at what it says. It says, the accepted model for nerve pulse propagation in biological membranes seems insufficient. It is restricted to dissipative electrical phenomena and considers nerve pulses exclusively as a microscopic phenomenon. The simple thermodynamic model that is based on the macroscopic properties of membranes allows explaining the more features of nerve pulse propagation, including the phenomenon of anesthesia that has so far remained unexplained. So who answered about knowing an anomaly of the action potential explanation? I thought so. I didn't know any either before I started wondering about this other model. So what's interesting about this, apart from knowing about new things, is that from the perspective of paradigms and science and books like Kuhn's Structure of Scientific Revolutions, there are anomalies that are often ignored when there is like a satisfactory explanation of phenomena. And then suddenly this other explanations come about, and these anomalies start popping out. As it turns out, it wasn't a very satisfactory. It's like when you're uncomfortable and you don't know you're uncomfortable, and then you're irritated, and then you're like yell at somebody. But that's a non-nerve phenomena as well, but that's not what I'll point out. It's just, it's funny how, and this brings it about, we don't know what we don't know. And we don't know what we don't know until somebody comes about with a better explanation. So what happens is, for example, the Heimberg and these people defending the Soliton model say things like these. The advantages of the Soliton model include a thermodynamic explanation of the effect of anesthetics, the induction of action potential by local nerve cooling. So look, so you can generate an action potential by cooling the nerve, which is pretty surprising. It doesn't have anything to do with electricity, or apparently it doesn't have anything to do with electricity. No? And there is physical expansion of the nerve while an action potential is happening. So you can actually measure the axon, and during the action potential, the axon contracts, like gets smaller. So those are pretty weird things that people are not talking about in the literature.
How much cooling, like what sort of temperature difference are we talking about?
I actually don't know.
Okay.
I haven't found that out.
Do you think there could be anything electrical involved in an expansion, such as like the change in concentration? Like if you have charges concentrated in the cell and it expands, wouldn't the charges be less concentrated?
Yeah.
Would that change the voltage?
the thing is, what's contracting and expanding is a membrane, so the charges are not really in the membrane.
The thickness of the membrane is expanding and contracting?
Yeah, but to the sides, right? So, no, well, it actually changes like this also, apparently. But since the charges are not in the lipids or in the proteins, it would be. So what you're saying is like the charges separate between each other and then come together, right?
I was imagining the entire cell expanding, and then that would make all the charges inside it less concentrated.
Okay, yeah, but what expands is really just like the membrane, right? So whatever charges are in the Gatorade suspended are going to stay wherever they are, and then just the membrane is going to expand, and very little. So, but your point about if we can give electrical explanations of these anomalies is very interesting, though. I mean, of course, most of the people that are working in biophysics at this level are going to try and give explanations of these anomalies from the perspective of an electrical phenomenon. They're going to say, well, you know, for example, I went to New York to see this like sacred researcher called John Renzel on the Hodgkin-Huxley model, and he said, well, you know, like it's actually ions like accumulating inside the membrane, so that could actually push, I don't know, the membrane in some way. Or, I mean, there are ways that you can try and explain this from the electrical perspective, certainly. I mean, you can try. And some are better than others.
Can't you also like do the reflexive and say, how can we explain the electrical with the heat? Like, because it's tempting to say, okay, let's try and explain this heat model with the electrical model, but you can also say, let's explain the electrical model with the heat model. Do you get what I'm saying? Like, it's tempting to use the current paradigm to explain the anomaly, but the anomaly can also create conditions in which the current paradigm is explained.
At least that's the question.
Yeah, let me advance a little bit more because it doesn't have to do with heat so much. So let me just give a small account of what the new model is about. And certainly, actually, I think that you would have to. Like, these guys are going to have to say how it is. They're going to have to explain what the Hodgkin-Huxley model already explains in order to gain respect. So, for example, something that happens that's very weird, and we can't explain from the traditional paradigm, is that if you take a bunch of tadpoles and you anesthetize them so they can't move, so you're there, you're seeing that they can't move, and you submit them, you put them in some sort of somewhere where you can increase pressure. You increase pressure and you reverse the anesthetic effect. So they couldn't move, you increase pressure, and suddenly they move again.
So, well, at least in, just like in chemistry, if you increase the pressure, it almost seems to have the same effect as heating it up with the just with diffusion. So, is that what they is going on, or is it just like not explained, or is it not that? It's probably not that simple.
I'll let you know what's going on. I just want to, this is what I'm trying to tell you is about weird things that we can't explain from the normal paradigm.
I feel like increasing the pressure would change something in the original model because it had temperature as one of the variables involved in the equation, and that would change when you increase the pressure, like she was saying. So I feel like that changing the pressure would change the results from the classical model, from my understanding.
I didn't explain myself if I, the Hodgkin-Huxley model doesn't have temperature as one of the variables.
The graphs that you showed us, it had different results for different temperatures.
Yeah, you do know that, but that's an external parameter. That doesn't mean that it's one of the important variables of the model. So you can't, it's going to affect the shape of the curve. It's something you have to take into account, but it's not, like voltage is not a function of temperature, so to speak. I mean, that's actually a good question. I'm gonna have trouble explaining that. The point is that the classical model uses only electrical variables. So it's about voltage, capacitance, and conductance. So those are the variables it takes into account. the considerations on temperature are to adjust the graphs that you obtain with those three variables to experimental results. And they do observe that if the temperature is different, the nerve behaves differently. But that doesn't mean that it's included in the explanation.
Do you want to put the equations up again?
Yeah.
Let's have a quick look.
So the variables are pretty much voltage, conductance, and conductance of the different ions, right? And these are time variables, and these are descriptions of the conductances. But
So temperature isn't an intrinsic variable in any of those equations.
so the point is that you cannot
Sorry, I was going to say conductiveness is affected by temperature.
conductance.
So it's indirectly a variable.
Yeah, I mean how fast the ions are going to move across is going to be affected by temperature. I mean, you're right in the sense that temperature is going to have something to do with the phenomenon to a certain degree. But what's going on here is that you are not, it's not that Hodgkin and Huxley didn't realize that temperature is going to have something to do with the phenomenon, but they don't consider temperature to be one of the fundamental variables that explain the phenomenon, so to speak, right? It has something to do, and you have to take it into consideration when you're trying to simulate, but it's not one of the crucial things causally speaking. So this is the pressure reversal effect, which is very interesting and it's hard to explain. And another thing that's hard to explain is that anesthetics, the effect of an anesthetic is found to be, anesthetics are more effective in as much as they are more soluble in lipids. And this is an empirical law, or an empirical regularity, a correlation, that is very difficult to explain from the Hodgkin and Huxley phenomenon. Actually, I spoke with a dentist that lives down in Carlsbad a year ago, and I was telling him about this, and he said that when they taught him about anesthetics, they taught him all these things about the nervous impulse and this bunch of things, and then when they turn to anesthetics, they go like, well, and by the way, anesthetics works like this and like that, and they never explain what the correlation is or what the relationship is between the understanding we have of nervous impulse and anesthetics. So this is something that is actually not understood properly from the traditional perspective. So this is what these guys from the new model are claiming to be explaining. So they're saying we have a new model that understands things in a different way, and we can explain something that Hodgkin and Huxley cannot explain. And so the model has to do with solitons. Solitons are a special kind of wave that has permanent form and does not annihilate or change after time, that this guy, John Scott Russell, discovered in 1834. He's from Edinburgh. And he was on his horse next to one of those channels, and a boat was being pulled by his horses, and the boat stopped, and it generated this wave that had a specific shape, and it carried on with that shape, and he started following the wave on his, riding the horse, and the wave, carried on, and he was tired of following it. And he was very impressed by a wave that did not eventually fade out. Fade out? Yeah. And he built in his backyard a channel simulator and started putting weights on it and exploring what the hell was going on with these waves, and characterized this solitary wave called the soliton. And there are solitons in nature. There are in River Severn in England. There's a wave that's very good for surfing because it doesn't change shape, but it carries on forever. It's like a dream of any surfer, right? And there are also some clouds in northern Australia that are solitons. So this is a picture of the wave. There's a whole discussion about if tsunamis are or should be considered solitons or not. And what they're saying, what these guys are saying is like, wait. Like the action potential is not, I mean, it has to do with voltage, but what's really going on is that it's like a sound wave that travels in the membrane. And how is this sound wave? So you know that like if you have chicken broth and you put it in the fridge and you take it out, it looks like the jelly that's disgusting and you don't want to eat it anymore. So lipids have this thing that they have a transition, they can change phase from gel to liquid. So what they're saying is that since the membrane has these lipids, then what's going on is that it locally becomes gel, and that local gelification travels like a solid zone through the membrane, right? So it's like a jelly goosebump effect. And though that when it becomes gel, the lipids have a certain structure that opens pores. And then the ions are actually, if they are crossing at all, they are crossing across these lipid channels instead of the protein channels, right? So that's more or less what they're saying. It's a pretty wacko thing. It sounds very strange for somebody that's been studying the traditional model for a while. But they do have a very good explanation for anesthesia. So these are the equations for the solids and model. So it's also dynamical systems theory what backs this up. And the variables are lateral density of the membrane. Some parameters are the sound velocity. This is a spatial variable, the position, right? And so if we compare the two models, one is saying that there is like a density change in the membrane, a local density change in the membrane that's going to travel. The other says that it's a purely electrical phenomenon. What's your name?
Amy.
Amy was saying like, hey, well, can't the new model explain the previous effects? And yeah, I mean, they say that this density change affects the capacitance of the membrane, and then that in turn changes some electrical properties, right? And their explanation of anesthesia is that the anesthetic lowers the freezing temperature of the lipids. So what's going on is that, and you can reverse it with pressure. So since pressure and temperature are associated in this thermodynamic model, then we can give an account of why it is that pressure affects the proclivity to have a nervous pulse. So it works very well for anesthesia. It doesn't work very well for a lot of results that we already have. I mean, protein channels apparently do exist. Like there's crystallography where we have actually more or less seen them. We know that we can separate the lipids from the proteins when we take a bunch of cells, we blend them, and then we centrifuge, and we have proteins on one side and lipids on the other. So these things actually exist. But what they're saying is they don't explain it, or they explain very little, say. So this is what is going on with these people, and the important questions are, so how do we know when we know? Like, what is it about our models that makes them true and forever true, or are there other options? Do we have two models that explain? Is this something like the wave account, the light as wave, light as particle dichotomy? What the hell is going on? And how is it that these neurons actually communicate? And how is it possible that we have, in 2014, another model suddenly arising that explains a phenomenon that we didn't explain before? And how should we behave with respect to a controversy like this? Do you think that one or the other model should be correct? Does anybody have any thoughts about this?
All of those models seem way too simple for the complexity of this phenomena, and it's seems like there's electrical aspects of voltage pushing charge, and it also seems like there's thermodynamic aspects of molecular collisions pushing the charge. Because ions are affected by voltage, but they're also affected when, thermodynamically another particle collides with them, it also pushes them. So it seems like they're affected by both, and it's kind of like either explanation is too simple for how complex it is.
That's an option. That's a very good option, actually. I vote for that now. But it is true that it could be the case. But what's interesting is that they're attributing, for example, you would have to be able to say, protein channels, what do they do? Are they two accumulative phenomena? Like, are ions crossing through proteins that have gates that change with voltage, and the lipids are turning into gel and opening other lipid channels, and other ions are crossing? So is it like, that would mean that they are like two different phenomena that integrate in the action potential, right? Both things are going on at the same time.
Yeah, like the positive, like in that picture, the positive on the outside and the negative on the inside, there's negative pieces of that protein that are going to be pulled towards the positive, and vice versa, there's going to be positive pieces of that protein that are pulled towards the negative. So the protein shape is going to be affected by the charge separation with voltage, but it's also going to be attracted or pushed by the membrane itself.
That is an option. I think it's hard to make sense of certain things, but I think that's likely. At least that's a perspective that's worth pursuing. What's more common between, is anybody majoring in neuroscience or studying neuroscience? From the neuroscientific perspective, people tend to think that this thermodynamic model is probably wrong. Just because we have such good evidence and such a good account of the voltage variation, only taking into consideration the ion channels, that it seems to be like very exaggerated to try and include all these other entities to explain something that we already explained. But on the other hand, the fact that this model explains anesthesia so well makes us want to think that there is some epistemic value in what they're saying.
There's a lot of, there's also a lot of medications, like psychotropic medications, that aren't known how exactly they work. And I think to some extent the sodium ion channel model has been exhausted as far as to what extent, like lithium, for example, doesn't even, like lithium's an ion, and it doesn't even, like I'm looking at my bio notes right now, and it doesn't even interact with cells the way these ions do. It blocks a certain, it blocks a certain protein cascade. So I guess it's just, and like that's the most basic of the medications for like bipolar disorder. So it's kind of weird because there's a paradox, I think, in neuroscience right now where it's like, the science says this, but then as far as what we're pragmatically using to like treat people and like in the world using like clinical trials, that we don't necessarily have a scientific explanation for. So I would say that like there might be evidence for this, but it might not be the full picture.
That's because this is a pluralist group. What did you do to them?
They're undergrads. Most undergrads.
I was expecting like,
later, it gets beaten out of us later.
We're a what group?
a pluralist.
But Natalia, we talked about this today, but when I had lunch with Heimburg for the first time, he sat me down and said, and since then I was, I've looked into this, but then you said something which disconcerted me today. But I thought the strongest piece of evidence is what we talked about at lunch today, that by removing the proteins, you still get exactly the same behavior. And I think there is evidence for this outside of their papers too. But I think that might be worth saying, unless you just think that there isn't the evidence for it. But I thought there was the evidence for it.
What I do know, that what there is evidence for, is that not that you can have an action potential understood as a voltage variation, but what does happen, do you know there's a patch clamp technique? That is, you take a pipette, you basically suck a little part of membrane, and you observe what moves across the membrane. And what you can do is that you take all the proteins away, and you check to see if there are ions crossing the membrane. And what you observe is that the same thing you observe when you have proteins, you observe when you don't have proteins. So what that shows is that there are lipid channels.
So there are lipid channels which could, all right. This is terribly confusing. Okay, fine.
So there are lipid channels. So if you're going to have
so then that moves the
crossing,
ions
you don't
around.
need this.
This moves the ions around. I just thought you got the same phenomenology of action potential. I don't want to believe you, but I have to go back and look at the papers. Okay.
Don't believe me.
Yeah. I'll go back and look at the papers, and we'll talk about it.
Yeah,
Okay.
absolutely. Yeah, well, basically what's going on is they're saying you don't need proteins.
Yeah, that's what they're saying.
Dynamic.
Exactly.
But they do, I think they do have trouble reproducing the whole, exactly the same phenomenon if they don't have the proteins. And then I had this slide where they give this catalytic role to proteins. So they're saying, well, proteins actually, they do play a role, not the role that we normally think. I mean, the fact that ions can cross through them is not the most relevant aspect. It's the fact that they change the melting point of the membrane. Somebody.
Does anyone else have something to say? I'm imagining evolutionarily this arising thermodynamically, and then the protein channels evolving to make it better. That's kind of what I'm imagining, but I don't have any evidence for that.
I don't know. I mean, truthfully, I am baffled by this. I don't know what ultimately is going to happen. What I do know is that this makes some things clear. For example, it makes clear that what the hell is the membrane? And what are the, like, I thought, I don't know, when I was an undergrad and I was taught about this and I studied the Hodgkin-Huxley model, I thought like we totally nailed, like humanity nailed it. Like we understand this phenomenon back to front. This is super clear. We even have like a artificial intelligence neuron in my screen. I can like simulate it. Like what else can you possibly want, right? And we imagine this membrane that is this bilipid layer super romantically and has these channels suspended, and the channels have gates. They don't have gates, but they have gates. And we have all this narrative about like how it is that the nervous impulse happens. And truthfully, like it starts getting reified. I'm sure that you've talked about that sort of thing with Rasmus. Like we start believing our own story to the point where we ignore the counter evidence. We forget to check if it's actually true. We forget to check if there are other things we cannot explain, and we're satisfied because we're limited. There's only so much information we can handle, and we get very excited when things happen to work out. So what is a mystery for me is what is the membrane and what is going on in the membrane. I have no clue. Like right now, I can imagine it in very many, like as a chicken broth with Gatorade inside, or like a bilipid membrane with protein channels inserted, embedded in it. And it depends on how you imagine it, the kind of explanation that you're going to derive. But what's clear is that, like, what's your name? Amanda? Amanda? Like Amanda says, the phenomenon seems to be, reality is so complex and so rich that what we do when we understand it is basically make a cartoon out of it. And then we believe our own cartoon.
Thumbs up. It might be worthwhile to point out the metaphors or analogies behind this. Like you have such a rich and nice story that for the Hodgkin-Huxley, the metaphor is like the nerve is like a electric wiring circuit, yes? For the soliton model, it's like the nerve is like air or water, a medium through which a wave flows. So those are two very different metaphors, or two very different analogies for thinking about how information, as it were, it is in a way, information, you can call it information if you like, is moving through the nerve from one end to the other. It's either like an electric circuit board or a wave moving through. And both of them are totally plausible. There's no a priori reason to delete one over the other, or even think one is necessarily better than the other. So I think it's interesting to think, tying it to Ray Gibbs's talk about metaphor, that there's a metaphorical aspect here too, that also can have this power over our imaginations and have power over scientists' imagination.
Yeah, and it accommodates evidence.
And it accommodates evidence.
So what are the consequences for neuroscience if this is
I don't know. What do you think? No
I
clue?
can't think of any. I don't fully understand this, but I can't think of like.
What could happen? Are you gonna answer her question?
Yeah, like unintended consequences of like medications and like treatments of like people with like epilepsy or any like neurological disorders. Like, I guess there's a lot of testing that goes on before treatments get approved, but also the lack of treatment, I guess is what I'm trying to say. Like, if we have the wrong model, we'll have the wrong explanations for diseases, and the diseases don't are treated.
So building, to be a little more concrete, I think Amy's exactly on the right track, Ryan. But to be a little more concrete, a standard sort of explanation that you're given in first year medical school as to why anesthesia works is that there's like this molecule that just like blocks the gate or something like that, the channel. Yeah, it just blocks the channel. But if the soliton model is right, then it has nothing, anesthesia has nothing to do with blocking the channel. Rather, it changes the medium through which the wave is moving, that is the cell membrane. So I hope you can see that it would make a huge difference for drug R&D, research and development, whether you're actually trying to, or you even think that the drug is like blocking the channel, or it's just changing the permeativity or whatever of the membrane. You see that? So in that sense, it would, that's just one example.
The inhibit-activate dichotomy is very alive and well in neuroscience. And I think that there's, like, even among the structure, the model that prevails now, given the amount of milliseconds that everything happens, there's even an ad infinitum, like, I don't even know how to go into it, but basically, like, the combinations of all the neurotransmitters and everything going, like, there's so many molecules transferring all the time that to try and, like, isolate it to try and treat it is really problematic to, even the way the current model gets utilized gets redefined in problematic ways that I think just can really, I don't know where I'm going with that. But
Yeah, it's difficult. Although, neurotransmitters are at the synaptic level.
Yeah, it's a whole
and
different level.
there's a different level. Neurotransmitter is a problem. Something that is surely a fact is that neuroscientists should be studying more, at least basic neuroscientists, like biophysicists studying the nervous pulse, should be studying more thermodynamics. That's a very clear consequence. Like, they should be, it's something that they don't teach us, they don't show us as neuroscientists.
And their paradigms can be an interesting, like, there's the electromagnetic paradigm and there's like a thermodynamic paradigm. And you learn the electromagnetic paradigm when you're learning about nerve impulses, and you don't really learn any thermodynamics.
Exactly. So apparently there are more thermodynamical effects involved that we are not exploring enough. And of course that has consequences in the practice. It has consequences on possible explanation, potential things we could be explaining and we're not explaining, and things that we're explaining in the wrong manner. And I think it also has consequences for neuroscience and the explanations, or for science in general. Something I really like about this example, and this is a personal sharing, is that we were talking with Tanner and Michelle earlier. psychology as a realm, neuroscience as a realm, psychoanalysis as a realm can explain about consciousness, right? So if you think that there is only one model, correct model for each phenomenon, and then all these correct models are going to integrate together, and they're going to form like this perfectly oiled machinery of understanding, and we're eventually going to get to the tapestry of the universe. We're going to decipher how everything works, and everything's going to be related to everything else. That's one way of thinking about scientific knowledge. And another way of thinking about it, and you said the correct model. And it could be the case that there is no correct model. I mean, one model serves us to exemplify the thermodynamic properties of the earth pulse. The other model serves us to exemplify the electrical properties of the earth pulse. And the phenomenon is so complex that we cannot give only one account. So we need to satisfy ourselves with these like models that work like little telescopes that reveal little parts of the phenomenon, right? A bit like the parable about the three blind old men touching the elephant, and one touches the ear, the other touches the mouth, the trap, and the other the tail, and each is giving a different account, but it's the same thing, right? It's the same animal, but our ability to get to the world and acquire knowledge of it is not good enough to get a complete account of everything or any phenomenon. Maybe we can for some phenomena, maybe we can't for other phenomena. And then in that sense, if something is complex, consciousness is complex. So why do we want to give one account of consciousness from only one field instead of recognizing that at the most we're going to have to solve concrete problems that have to do with consciousness from different perspectives that do not have to integrate into only one. So I'd like to just finish with this and so you get your midterm. So one perspective is monist and the other is pluralist, right? Monism would be there is only one correct account of each phenomenon, and a pluralist is an account where we actually approach reality piecewise. So I like this painting by Picasso because Cubism has like each eye is given from a different perspective. I mean, we eventually figure out this is a person, or we're not seeing from only one perspective, which is what monism would desire, but we don't get such a beautiful picture of reality either. So according to the monist picture, you would have to, there's only one phenomenon, right? There's only one personality. They have to fight to see which one it is, right? And from the perspective of pluralism, we have tools. There's a toolbox of science. So we can use different models for different things. It depends what you want to do. So this is just to illustrate like what this debate in philosophy of science goes about. And I'm going to leave you with, this is a quote by the guys that are doing the solitude model. It says, it seems likely that a view will eventually emerge in which the conductance of biomembrane is seen as a feature of a lipid protein ensemble rather than as a feature of single proteins. This implies a strong coupling to the macroscopic thermodynamics of the biological membrane as a whole. So this goes along with what she was saying, and I'm going to leave you here. So, I hope you at least know why somebody got the Nobel Prize. Thank you.